This is the logistic regression module on model fitting. For our purposes, model fitting can usually be thought of as a black box. R can figure out which set of beta coefficients leads to the best fitting model, and that's all there is to it. As general background, and because you might encounter this terminology as you read the literature, for logistic regression, what R does isn't to maximize the sum of squares associated with the model, but instead is doing something similar, which is to maximize something called the likelihood function. We don't have to precisely worry about precisely what this function is, and indeed for continuous outcomes, maximizing the likelihood function and maximizing the model sum of squares are equivalent. These two concepts aren't equivalent for logistic regression, but it does no harm whatsoever to imagine that what R is trying to do is essentially the same thing as what you're used to seeing for continuous outcomes. However, what is important to know is that in logistic regression, what R ends up doing when it's fitting a model is applying an iterative procedure, rather like a cat chasing its tail. Sometimes this procedure can go badly wrong, causing R to give up and to produce some cryptic error message. In almost every case, what it's trying to tell you is that there's something wrong with the data, and this slide lists the things to look for. These things are all related. Looking at the first, if every female in the data set has a positive outcome and every male a negative one, R won't be able to estimate the impact of gender. Indeed, it should be intuitive that this impact is infinitely strong. For a single predictor, this phenomenon will be obvious on examination. For multiple correlated predictors, one of the things that can occur is after the predictors are cross-classified, some of the cells will be very small, and you'll end up with the equivalent of all the females having one outcome and all the males having another. The smaller the number of predictors, the smaller the number of patients, the more the predictors, and the more highly correlated those predictors are, the greater is the likelihood that this kind of problem will occur. Continuing the analogy with continuous outcomes, for continuous data, what we did to determine whether a predictor mattered was to fit a reduced model with all the relevant covariates, fit a full model with those covariates plus the predictor or predictors in question, and use a partial F-test to compare the two. If the fit of the full model was much better than the fit of the reduced one, we declared the predictor in question to be statistically significant. For logistic regression, the same overall logic applies. We still have two nested models, and we still compare the fits of the two. For a continuous outcome, the fit is quantified using the model sum of squares, whereas for a dichotomous outcome, it's quantified using something called -2 log L, which can be read directly from the printout. When making the comparison for continuous outcomes, you use a partial F-test, whereas for dichotomous outcomes, you use a chi-square test. This chi-square test has a single parameter, namely difference in degrees of freedom associated with the full and reduced models. For example, when assessing the impact of a single continuous predictor, the difference in degrees of freedom is 1. The chi-square statistic is the difference in -2 log L between the full and reduced models. Large values of this chi-squared statistic indicate statistical significance. For continuous outcomes, there's only one version of the partial F-test to consider, whereas for dichotomous outcomes, there are multiple versions of the chi-square test. The likelihood ratio test that we just described is often considered to be the gold standard. One of the silver standard tests is printed from the summary function. This test is based on taking the regression coefficient divided by the standard error. For continuous outcomes, doing so is identical to performing a partial F-test. For logistic regressions, the results aren't identical, but are usually very close. As a matter of fact, will only differ markedly when the data set has other characteristics that should make you worry, such as a small sample size relative to the number of predictors. Confidence intervals for logistic regression are based on assuming normality on the logit scale, which in turn implies the sample sizes are moderate to large. For a 95% confidence interval on the logit scale, take the regression coefficient plus or minus 1.96 standard errors. To put things on the odds ratio, hit the E button on your calculator. The resulting confidence intervals will be symmetric on the logit scale, but asymmetric on the odds scale. And you should get help if you're trying to apply logistic regression to very small data sets.